You may have read or heard in the news recently that the spring of 2020 is reckoned to have been the sunniest in the UK ever, or at least since records began. Now, the sun is always shining. There it is, up there. And there's nothing that we here on Earth are doing to change that. The sun will continue shining, at least for several billion years, before it eventually dries up, expands, and destroys all life in the solar system. But hey, that's for another lesson. But the reason for the record spring is not how much the sun is shining, but how much sunlight has reached the surface of this planet on this little particular part of it that we call the United Kingdom. And that could be, at least in part, down to us. Just like the oceans, the atmosphere of our planet contains currents or streams of air flowing round the planet. The exact position of these currents depends in part on the temperature of the planet's surface, especially our oceans. These streams can drag moisture-rich air over parts of our land, for example Africa, causing the annual flooding or rainfall events. Warming or cooling of the oceans as the airflow passes through them can cause these streams in the air to shift north or south, and so therefore affect where the rainfall eventually ends up. Changes in the direction of these streams is thought to be in part responsible for some of the dreadful droughts experienced in parts of Africa during the 1980s, for example. Just Google the Ethiopian famine for more information on that. The jet stream is a plume of air currently overhead in Britain. Usually it shifts around during the seasons, and so we experience more cloud form, rainfall, or sunshine, depending on exactly where it is over the British Isles. At the moment, however, it is locked in place and has been so for at least a month, bringing warm, dry air with very little moisture and therefore very few clouds over our country. If there are no clouds, of course, that means more sunlight is able to get right down to the surface of the Earth and therefore warm it up. Earlier in the year, however, the same jet stream brought cold, wet air over the surface of the British Isles, resulting in prolonged and torrential rainfall, flooding and storms that we experienced in winter 2019 to 2020. The gradual heating of our atmosphere, what we call global warming or global heating, affects the strength and the position of these currents in the atmosphere, and so therefore affect our weather patterns. It seems likely that we are going to experience more extreme weather conditions, for example, longer, drier droughts, but also wetter, longer rainfall events resulting in flooding in the years to come, rather than a nice, predictable weather pattern. Three graphs on this page all show studies made on the average global temperature from the mid-1800s until the present day. All three of them obviously show that there has been an increase in temperature of about 1 degree centigrade throughout that time. Now that doesn't sound like a lot, but if you imagine the amount of energy that must be taken in order to warm up the entire planet by 1 degree, hopefully you can appreciate that it's an awful lot of energy having to go in to do that. In other lessons, we'll look at the impact of that amount of energy and that temperature change that it has on our weather systems and planetary processes. But for today's lesson, we'll look at what is causing this temperature rise. Scientists have discovered that certain gases have been found able to trap heat energy in the Earth's atmosphere and not allow it to escape back into space. The concentration of these gases is increasing in the atmosphere, and so more and more heat energy is being trapped, and this is causing the average temperature of the Earth to increase. As it does so, it has an effect on our weather patterns. It causes oceans to warm up and expand, and it causes ice to melt, and that is leading to global sea levels rising. We call these gases greenhouse gases because they cause the greenhouse effect. The greenhouse effect happens because some gases absorb infrared energy released from the Earth's surface. This traps the heat in the atmosphere in the same way that windows trap the sun's energy inside a greenhouse or a conservatory. Like most of the energy on the planet, that energy comes from the sun, but in a different form. The sun releases energy in the form of heat as short wavelength, ultraviolet light. 60% of this light that reaches the planet's Earth passes straight through the atmosphere and warms the surface of the Earth. The gases in the atmosphere can't trap the heat energy at these wavelengths. So, this UV wavelength energy passes straight through the atmosphere and warms up the surface of the Earth. But at night, this energy is released back into the atmosphere from the Earth. But it's released not as short wavelength ultraviolet energy, but as long wavelength infrared energy. So the amount of energy being released is roughly speaking the same, but it's coming back into the atmosphere in a different form. And the greenhouse gases in our atmosphere are able to absorb energy at these wavelengths, and so they trap some of that energy in the atmosphere. We've discovered that covalent bonds in molecules have set distances between them, and some molecules have a bond length between the different atoms that's at exactly the right length to trap the long wavelength radiation, causing these bonds to stretch and bend more vigorously. It gives the molecules more energy. More energy in the molecules means more heat energy in the atmosphere. The main greenhouse gas molecules in our atmosphere are carbon dioxide, methane, and water vapour. There are several other gases, such as carbon monoxide, which also have an effect. The amount of water vapour in our atmosphere hasn't changed very much in the last hundreds of millions of years, if not billions of years. So actually, our Earth is perfectly adapted to being able to cope with the sort of global warming that has been caused by water vapour molecules in the atmosphere. However, it's not quite as easy as that. Whilst the concentration of water vapour early on hasn't really had any kind of extra impact on global climate change, as our Earth heats up, more water is going to evaporate from the surface of the oceans and rise up into the atmosphere. As it does so, of course, it will start contributing to global climate change because there'll be more water molecules than normal, and so therefore more of a greenhouse effect because of these particular molecules. Carbon dioxide is well known as being the most abundant greenhouse gas after water vapour and is the one most linked with human activity. This graph here shows the thousands of years before present, up to 800,000 years before present, clearly showing that the concentration of carbon dioxide in the atmosphere has stayed relatively level at between 200 and 250 parts per million until the mid-1800s, where it started to rise up to now to a level of 400 parts per million. That links with the period of time in which we started burning many more fossil fuels, coal, oil, and natural gas. And we know from our last topic of work that carbon dioxide is one of the main chemical products from burning these hydrocarbons. This graph is looking at a shorter time scale from the 1960s to the early 2000s, but again clearly shows that the concentration of carbon dioxide in the Earth's atmosphere is increasing, and it also, with the blue lines, shows how that corresponds with an increase in global temperature changes over the same period of time. You can see that the trend of the two graphs matches up. This graph too takes both temperatures and the concentration of carbon dioxide in the atmosphere and matches them up. But this is from a series of studies that are able to go back hundreds of thousands of years before the present day. So you can see that although temperatures and carbon dioxide concentrations have changed in the past, and not due to human activity that we know of, that since the 1800s, the concentration of carbon dioxide has increased massively to a concentration much higher than it has been for hundreds of millions of years before, and that also has caused an increase in the temperature too. In summary, the average global temperature is rising. This is caused because short wavelength radiation from the sun passes through the atmosphere and warms up the Earth's surface. At night, this energy is released from the Earth's surface, but as long wavelength infrared radiation. Certain molecules in the atmosphere are able to trap the energy from this long wavelength energy and cause the atmosphere to heat up. These molecules include water vapor, carbon dioxide, and methane. But other molecules, such as nitrous oxides and carbon monoxide, are also powerful greenhouse gases. And we have done studies and can see that many of these gases have increased in the atmosphere because of human activity.